Chapter 2 in our text starts to get a little more exciting as we actually get to start doing some math, start doing some descriptive statistics. We're going to look at a lot of different types of descriptive statistics as we attempt to answer the essential question: how do we express and interpret descriptive statistics? And there are lots of different ways we can do that, and we're going to kind of start going through different types of ways we can describe statistics. One of them is we can organize the data in what's called a stem plot, also known as a stem and leaf plot. Let me show you kind of what I mean by that. Let's say I took some exams and scored them. And let's say the scores were 33, 49, 53, 55, 63, 68, 69, 72, 74, 80, 88, 88, 92, 94, 94, and 100. The whole idea behind a stem and leaf plot is we're going to split the data up into stems and leaves. So the stem is going to be the first part of the number. So the 30, that covers the first part. The leaf is the rest of it. 3, so we would get 33. For the 40s, we've got 49, so we put 40 for the stem and 9 for the leaf. In the 50s, we have 53 and 55. So the 50 is the stem, and the 3 and the 5 are the leaves. So there's two numbers there that represents 53 and 55. And we can keep going down following this pattern. We've got the 60s. We've got 63, 68, and 69. In the 70s, we have 72, 74. In the 80s, we have 80, so we need a 0. 88, 88. And then in the 90s, continuing on down, in the 90s, we've got 92, 94, 94, and 100 has a stem of 10 and a leaf of 0. So notice the leaves become the last digit. And just to make sure it's really clear, we'll include some type of key. And usually we do the first entry. 3-3 is 33. And the stem could be the whole number, the leaf could be the decimal. The stem could be the tens, the leaf could be the ones. A lot of different ways to do it. But the idea here is this makes a real quick visual so we can see where the clumping of data is. We can see if any data don't match the rest. In fact, that is interesting to us. Data that doesn't match the rest we call outliers. An outlier is a value that does not fit the rest. And one thing we might notice is this 33 value is significantly separated from the rest. And so we might hypothesize that 33 might be an outlier. It might be way out from the rest of the data. So that's stem and leaf plots, or stem plots. Another type of plot that we do are called histograms. And histograms are similar to bar graphs, except that they are continuous boxes, meaning the boxes are connected, they touch each other over ranges that show frequencies. So let's make a box plot for those exam scores that we just saw. I'm sorry, a histogram for those exam scores we just saw. Again, just so that I have them on the screen, the exam scores were 33, 49, 53, 55, 63, 68, 69, 72, 74, 80, 88, 88, 92, 94, 94, and 100. And there's a lot of mathematical ways you can decide how wide to make the bins. We could spend a lot of time on it, but really the general idea is the same. You want to have several bars, not just one or two bars. That wouldn't be informative. But have several bars that represent all of the data. But we don't want too many that there's only one in each frequency. So let's go in groups of maybe 15. So we'll go from 30 to 44.99. So 45, 60, 75, 90, and 105. So that's going to give us 1, 2, 3, 4, 5 bars. 5's probably a minimum that you would want. You could have maybe done this in tens or however you might want to do it. But for the first bar, from 33 to 44.9999, the number 45 goes with the right side. There's only one value there. So we'll have a frequency of 1 between 30 and 44.99999. From the 45 to 59.99999, you'll notice there are 3 values there. So that bar is going to go to 3, and notice the bar touches, so we can see that range. From 45 to 60, there are 3 data values. From 60 to just shy of 75, 1, 2, 3, 4, 5 data values. From 75 to 90, 1, 2, 3, 4, nope, just 3, I'm sorry. 1, 2, 3, going to 90. And then finally the 90 to 105, there are 4 values in there. And so we end up with this histogram that shows the y-axis, the frequency of the various range of scores. So that's a histogram, split up into frequencies within a certain range of values. Another way we can show some descriptive statistics visually again is with what's called a box plot. Box plots are also called box and whisker plots. But before we can get into finding and describing what a box plot looks like, we need to know a little bit of vocabulary. First, we need to know, I don't know what's going on with my labeling here. Let's see. First, we need to know what the median is. The median is the middle value when ordered. So we put the numbers in order, and we find the middle one. That's the median. The way on the box plot we're going to represent the median is with a dotted line. Another value we need to know is Q1, which stands for the first quartile. Quartile is the quarter. We want to split it into quarters. So the median split it into half, so we want the bottom, the middle of the bottom half. So the middle below the median. And we'll note that with a solid line. Q3, that's the third quartile, where 3/4 of the data is below that, is the middle of the values that are above the median. This one will also do a vertical line. So let's take a look then again at the exam scores that we've been working with throughout this example. We've got 33, 49, 53, 55, 63, 68, 69, 72, 74, 80, 88, 88, 92, 94, 94, and 100. Did I get them all on one line? Yep, they're all there, all 16 values. And they're all in order, which is nice. So the median is going to be the middle score. So if there's 16, the way we find the middle score is we take the number plus 1 and divide by 2. That'll get us right in the middle. So there are 16 values. 17 plus 1 divided by 2, or I'm sorry, 17 divided by 2 is 8.5. So 1, 2, 3, 4, 5, 6, 7, 8.5. The median is going to be between 72 and 74. Well, when we have two values in the middle, we take the average of them. So we'll do 72 plus 74 and divide by 2. The median then is going to be 73. Now for the Q's, the Q1 and Q3. Q1 is the middle of the bottom half. There are 8 in the bottom half. So 8 plus 1 is 9. 9 halves is 4.5. So it's between the 4th and the 5th value. So again, we're going to go 55 plus 63 divided by 2 is 59. That's going to be our Q1. So Q1, quartile 1, 1/4 of the data is below 59. 3/4 is above. Similarly, on the top half, again, there's 8 values, so it'll be between the 4th and the 5th value. So again, we do 88 plus 92 divided by 2 is 90. So that's our 3rd quartile. Also of interest to us are the low and the high values as we make our box plot. So here's a number line. So let's go 30, 40, 50, 60, 70, 80, 90, 100. And we're going to do a dotted line at 73 to represent the median, a solid line at 59 and at 90 to represent the quartiles, and then we connect the box through that. So that's where we get the box. The whisker then goes out to the low value of 33 and out to the high value of 100. This gives us a visual display of how the data is split up. We can now see that 25% of the data, or 1/4, falls in each section of the box and whisker plot. So 75% of the data is above that 59. 50% is below the 73. We can really easily split it up into fourths or quarters or quartiles using the box plot. Now, speaking of box plots and quartiles give open to the conversation about what is called the interquartile range, or as we like to call it, the IQR. Basically, how big is that interquartile? How much is between each of those quartiles? How much is in that middle 50%? What is the range of that middle 50%? Basically, we take Q3 and subtract Q1. So in our case, the interquartile range, Q3 is 90, minus Q1 is 59. That's going to equal 31. And so we will say that the interquartile range is 31. And the nice part about the interquartile range is it gives us one way to find these outliers. The outliers which will be outside of Q1, the left side, minus 1.5 times the IQR, or Q3 plus 1.5 times the IQR. Basically, each whisker is only allowed to be 1.5 times the box. Otherwise, the whisker is too long. So if we wanted to find out the left side, Q1 we said was 59 minus 1.5 times the IQR of 31. This would give us the lowest acceptable value for our data. In this case, it's 12.5. And Q3 is 90 plus 1.5 times the interquartile range of 31. 90 plus 1.5 times 31 is 136.5. What this is saying is outliers will be outside of that. Outliers will be smaller than 12.5, or outliers will be bigger than 136.5. Anything else we consider close enough to be valid. We don't have any values here, so we're going to say there are no outliers in this data set. So we kind of thought 33 might be because it was far away, but apparently it's not far enough away, now that we've got more of a mathematical way to get at the outliers. So that's the box plot and the important conversation about quartiles, splitting the stuff up into percents, 25%. We can actually go a little bit further with that conversation and talk about percentiles, or the percent of values below a given value. So let's go back to those same exam scores as we set this up again. I keep writing these down. You don't have to because you might have them on your notes, but they're off my screen. So again, they are 33, 49, 53, 55, 63, 68, 69, 72, 74, 80, 88, 88, 92, 94, 94, and 100. And let's make a frequency table here. And let's break it down into tens. 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99, and 100 to 109. And we'll do the frequency. There was one value between 30 and 39, one value from 40 to 49, two values in the 50s, three values in the 60s. Oops, two values in the 50s. 2 values in the 70s, 3 values in the 80s, 3 values in the 90s, and 1 value at 100 and higher. To help us see the frequencies, to help us see the percentiles, we're going to look at the relative frequency of each. There are 16 data values, so 1/16. The relative frequency is 0.0625 for the first two. 2 out of 16 is 0.1250. 3 out of 16 is 0.1875. 2 out of 16 is 1250. 3 is 1875. 3 again is 0.1875. And 1 is 0.0625. Still need the cumulative relative frequency for our table. So if we start to add these up, we start with 0.0625 plus 0.0625 is 0.1250 plus 0.1250 is 0.2500 plus 0.1875 is 0.4375 plus 0.1250 is 0.5625 plus 0.1875 is 0.7500 plus 0.1875 is 0.9375 plus 0.0625 is 1.0000. All right, so now we have a frequency table. We're ready to start talking about percentiles. If we wanted to find the 80th percentile, we want to find out where this graph hits 80%. 80%, notice on the third from the bottom, the 0.75, we're not quite to 80%. So we actually made the jump to 80% between 90 and 99. That's when we passed 80%. So the 80th percentile is going to be in that category. If we wanted to find the 15th percentile, where do we pass 15%? Well, 12 was just shy, so we must pass it here at the 25%, so the 15th percentile is between 50 and 59. We can even find quartiles this way. Q3. Well, Q3 really means 75%, 3/4 are below this value. So where does 75% occur? We actually know exactly where 75% occurs. It happens between 80 and 99. I'm sorry, 89. So that tells us that these values, what percent fall below them. Going the other direction, let's say what percentile is 69. Well, 69, the cumulative frequency there, if I'm scrolling too far here, it's the fourth one down, the cumulative frequency, it is in the 43rd, actually I'm going to round that to the 44th percentile. In other words, 44% of the data values are below 69 percentiles. Percentiles can tell us where we are all over the data set, but what we're usually most interested in is the center of the data set. So I want to talk about some measures of center. And the first measure of center is the biggest, most common one. We're going to spend almost the rest of this course talking about is the mean. The mean is what we get if we add the values together. And the way we're going to represent adding the values is we'll say the sum of the x's, that notation. That thing's called a sigma, capital sigma, and it means sum, or add up all of the values together and divide by the number. How many numbers did we use? Now we're going to use two variables to represent the mean. You might see x bar, or you might see this Greek letter mu. It's like the letter U with an extra tail on the left side, mu. And the difference is we use English letters, x bar, to represent samples, and Greek letters, like mu, to represent populations. So mu is the population parameter. X bar is the sample statistic. They both represent the means, but they're talking about different groups. So mu or x bar, the equation we're going to use, we're going to sum the x's and divide by the number of data values. So for example, let's say the values are 1, 1, 1, 2, 2, 3, 4, 4, 4, 4, 4. When we add them all up, when we get the sum of all the values on our calculator, that's 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 4 plus 4 plus 4 plus 4. We sum those all up, we get 30, and then we divide by the number of things there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 values, so we divide by 11. 30 divided by 11 is going to give us an average, or a mean, of 2.73, approximately. Probably should have labeled that example A, because I do have an example B also under that. Sometimes rather than adding up all the values, it's easier to work with the frequencies. And with frequencies, we change the formula slightly. We're going to say it's the frequency times the value. The sum of those divided by n. Here's what I mean by that. Let's make a column for the x's and a column for the frequencies. X's were 1, 2, 3, and 4. Frequency-wise, we had 3 1s, 2 2s, a single 3, and 5 4s. Notice the formula has the frequency times x. So we're going to make a new column for the frequency times x, where we multiply these together as we calculate our weighted average. 1 times 3 is 3, 2 times 2 is 4, 3 times 1 is 3, and 4 times 5 is 20. We want the sum of the frequencies times x's, and so the way we get the sum is we add the fx column together. When we add those all together, we get 30. So we get 30 divided by, there's still 11 numbers, and if you're not sure, add up the frequencies. And 30 divided by 11 is still 2.73. So if we have frequencies, you'll multiply the frequency times the number instead of adding up all the individual numbers. Quite often, especially with large data sets, this is a lot quicker to do. So measures of center, that's the mean. Add them up, divide by how many there are. There are 2 other measures of center. We don't spend a lot of time with them in statistics. One of them is called the median. We've already talked about that. That's the middle value. And the other one is called the mode. And this is the one that occurs most frequently. And it becomes useful in qualitative data. Because it doesn't make sense to find an average car color. You can't add up all the colors and divide by the number of colors, because you can't add blue and red together. That doesn't make sense. But we can talk about the mode being the most frequent color being the average of that qualitative categorical data. I want to have a really brief discussion once we find mean, median, and mode about whether or not the data is skewed. First, the opposite of skewed is symmetrical. A symmetrical data, you can cut it in half. The mean, the median, the mode, they are all the same. A common picture of a symmetrical distribution would be it'll be flat, it'll peak up in the middle, and it'll be flat. But the mean, median, and the mode are all the same. The left and right side are mirror images of each other. That is a beautiful symmetrical distribution. Now, usually it's going to be skewed. Skewed left means we have pulled extra data to the left. Something that is skewed left is going to have a look like this. Notice the extra data on the left side. It's got this pulled, stretched out left side of the data. Here, the mean, median, and mode are not the same. In fact, the mode is going to be to the right of the other two values. The mean is to the left, skewing it left. Similarly, we can skew the other direction, skewed right. That's when we pull the data to the right. So there's not much on one side, but on the right side there certainly is a lot more stuff going on. We are going to do a lot with skewedness, but I do want you to be aware of the vocabulary as it comes up from time to time. All right, so we've talked about this idea of measure of center, where we find the middle of the data, but there's an important piece that is missing still. If we know where the middle is, that doesn't help us as much unless we know how spread apart the data is. In other words, we're asking the question is, how close is everything to the mean? If everything is grouped really close to the mean, that means one thing. That means the data is pretty consistent. If everything is spread out wildly and unpredictably, that means something else about our data. And so to help us measure this, we use this thing that is called the standard deviation. The standard deviation, which calculates essentially, and I'm using these words loosely, the average distance to the mean. How far away on average are our data values from the mean? Now, what we want to be careful of with standard deviation, though, is which formula we use. If I have the formula S equals the square root of the sum of x minus x bar over n minus 1, what I want to notice, I used S, I used an English letter. That's the standard deviation of the sample. Versus we have a very similar formula which uses the Greek letter, lowercase sigma. It looks like a 9 on its side almost, maybe a little more curvy. Sigma is equal to the square root of the sum of x minus mu, notice the Greek letter again, over n. This is the standard deviation of the population of everybody. So if we only have a sample that we're taking, we need to use the formula on the left with S for standard deviation. If we're talking about everybody in the entire population, we'll use the formula on the right. So let's take a look at an example. Let's say I've got the data 4, 7, 8, 5, and 2. Now the way I'm going to calculate the spread of this data, I don't want to lose my formula up there. Again, this is a sample, not the population. There's more than 5 people in the world. So I'm going to list my x's, list my values of 4, 7, 8, 5, and 2. Now one thing you'll notice is the formula does have this x bar in it, or the mu, depending on which formula you're using. That's the average, remember. We talked about that earlier, the mean. So I'm going to calculate x bar, which we'll get by adding up all the values, 4 plus 7 plus 8 plus 5 plus 2, and I'm going to divide by 5. So the average is 5.2. And I fill that in all the way down. So working my way out from the formula, next it's x minus x bar. So I'm going to do x minus x bar and make a new column. We're going to subtract 4 minus 5.2. That's negative 1.2. 7 minus 5.2, that's 1.8. 8 minus 5.2, that's 2.8. Five minus 5.2, that's negative 0.2. 2 minus 5.2, that's negative 3.2. You know what I just noticed? I wrote the formulas down wrong. The formulas should have a squared in them. Please add that squared to both formulas. That's important. Square. The standard deviations have to be squared. So now if we move out of the parentheses, the next thing is we have to square that value. So now we're going to find out what x minus x bar squared is. So negative 1.2 squared should be a positive 1.44. 1.8 squared is 3.24. 2.8 squared is 7.84. 0.2 squared is 0.04. And negative 3.2 squared is negative 10.24. Now we've got that sum. The formula wants us to add all of that together. I'm going to have to scroll it off the screen just a bit. We're going to add, should be a positive, shouldn't it? A negative times a negative is a positive. We're going to add all of these together. 1.44 plus 3.24 plus 7.84 plus 0.04 plus 10.24. Add that all together, we get 22.8. So the sum, that highlighted part, is 22.8 divided by n minus 1. N is the number of data values. So there's 5 values. N minus 1 is 4. So we're going to divide by 4 is 5.7. And then take the square root of that. When I do, we get 2.39 when we round it. So the standard deviation of my numbers, 4, 7, 8, 5, 2, is 2.39. In other words, the average distance to the mean of all the values is about 2.39 units. Now we can tweak the standard deviation formula just a little bit if we also look at frequencies. So instead of listing out the numbers, we know the frequencies of the numbers. If we know the frequencies of the numbers, the formula changes slightly. For the sample, the standard deviation is now the square root of the sum of the frequency times the difference, x minus x bar squared divided by n minus 1. Or if we're dealing with a population, sigma is equal to the square root of the sum of the frequencies times x minus x bar squared over the number. Again, the big difference is with the population, we only divide by n the number. So let's do an example. Let's list some data and some frequencies. Let's say 9 showed up once, 9.5 showed up twice, 10 showed up 4 times, 10.5 showed up 4 times, 11 showed up 6 times, and 11.5 showed up 3 times. I like to include a column for x bar just so that I have a reference point, the mean. So we're going to do 9 times 1 plus 9.5 times 2 plus 10 times 4 plus 10.5 times 4 plus 11 times 6 plus 11.5 times 3 to get the total sum of 210.5. Remember, as we find the means, we're going to have to multiply the data times the frequency and add that up. By the way, the frequency of 1 plus 2 plus 4 plus 4 plus 6 plus 3, there are 20 data values. So when we take 210.5 and divide by 20, we get x bar, or a mean of 10.525. 10.525, 10.525, 10.525, 10.525, 10.525. So that's x bar. Now we start working out on our formula. X minus x bar. So that's the data values are our x's. So we're going to start with 9 minus 10.525 is negative 1.525. 9.5 minus 10.525 is negative 1.025. 10 minus 10.525 is negative 0.525. 10.5 minus 10.525 is negative 0.025. 11 minus 10.525 is 0.475. And 11.5 minus 10.525 is 0.975. Going out on our formula, now we see that that difference is squared. So we'll make a new column for x minus x bar squared. So 1.525 squared, and I'm just going to round it for the sake of conversation to 2 decimal places. 2.33. 1.025 squared is 1.05. 0.525 squared is 0.28. 0.025 squared is almost 0. In fact, I'm just going to use 0 because it's so close to 0. It's 0.000625, and I'm only doing 2 decimal places. 0.475 squared is 0.23. 0.975 squared is 0.95. Keep going. We got to multiply by the frequency. So now we've got another column for the frequency times x minus x bar squared. In other words, we're going to take the frequency column and multiply by the column we just found. So 1 times 2.33 is 2.33. 2 times 1.05 is 2.10. 4 times 0.28 is 1.12. 4 times 0 is 0. 6 times 0.23 is 1.38. And 3 times 0.95 is 2.85. And the next part of the formula tells us to find the sum of all of that. We're going to add all of that together. 2.33 plus 2.10 plus 1.12 plus 0 plus 1.38 plus 2.85. And that gives us 9.78. So our formula, given this came from a sample, is the square root of all that stuff we just found, 9.78, divided by n minus 1. Remember, n, the number of data values, was 20. So divide by 19. So we're going to take the square root of 9.78 divided by 19 is 0.7175. Our standard deviation here is 0.7175. Now, this process isn't really hard. It might take a lot of paper and a little bit of time, but it's not hard. I want you to be able to do this process comfortably by hand for our homework. However, you can, when the data values get to be many, do it on the calculator as well. So let's take a look at what that looks like on the calculator. On the calculator, there is a stat button right next to the arrow key. And the very first option that will come up is the edit option. If you click edit, it will give you some list that we can edit. And I want to actually clear out. There's some data in here that somebody was doing before. If I scroll up to highlight L2 and I hit clear, enter, it clears out L2. Let's go ahead and clear L1. Highlight L1 and hit clear, enter, and now it's empty as well. So now I'm ready. What I'm going to do in L1 is I'm going to list out the data values that we are working with. Let's do that first example where we did 4, 7, 8, 5, and 2. 4, enter, 7, enter, 8, enter, 5, enter, 2, enter. Then we're going to hit second, and the button right next to it, quit, takes us back to the home screen. Now we're ready to calculate the statistics that are related to list L1. The way we calculate those statistics is we go back to Stat and scroll over to Calculate. The first option there says one variable statistics. Hit Enter. It's going to ask you what list you want. If you hit second and then the number 1, it'll stick list 1 there. Don't worry about frequency list and go ahead and hit Calculate. If you're on a TI-83, it'll just type in one variable stats and you just type in L1, enter. It's a little quicker. And it gives you those single variable stats. And you see X bar is the first thing on there. X bar is 5.2. That's the mean. Notice that's the same mean we came up with in number 1 of 5.2. Going down, you'll see the sum of the x's is 26. The sum of the x squareds, we didn't really use that. Then you've got Sx and sigma x. Remember, Sx is the sample standard deviation. Sigma is the population standard deviation. So I need to decide at this point, is this the sample or the population? We said it was a sample, so Sx, the sample, is 2.39, which is the same sample standard deviation that we found in part 1. So nice little trick on the calculator. I do want you to know how to calculate it by hand, but you can use the calculator as well to check your work. So standard deviations, I want to play with this idea a bit now that we know how to calculate them. Standard deviations, once we know how to calculate them, we want to make sure we understand what they mean. Standard deviation tells us how close we are to the mean, which means if I am z standard deviations from the mean, I can figure out what data value that is by taking the number of standard deviations times the standard deviation plus the mean. Or if it's a sample, z times s plus x bar. Sample or population, it's the same idea. So what I mean is, if I know the mean of a population is 8, and the standard deviation is 1.2, I can find a value that is 1.7 standard deviations from the mean. The number of standard deviations from the mean is what we're going to call our z-score, or our z-value. We're 1.7 standard deviations from the mean. So x, our value, is z, 1.7, times the standard deviation of 1.2, plus the mean of 8. So 1.7 times 1.2 plus 8 gives us 10.04. A value of 10.04 would be 1.7 standard deviations away from the mean. Essentially, we have a way to measure distance from a mean. We can go below the mean also. We're going to find a value that is 3 standard deviations below the mean. Again, the number of standard deviations away, that's our z-value. So x is 3 standard deviations, which is 1.2, away from the mean. Now the catch is, here we've got the word below. When we are below the mean, the z-score has to be negative. That gets us 3 standard deviations, or 3 steps below the mean by subtracting, a negative z-score. So here we have negative 3 times 1.2 plus 8. And that's going to give us 4.4. Lost my number 1 there, sorry. Things have been disappearing on this video. I'm not sure why that is. So really, standard deviations give us a way to compare on a normal standardized scale how far away from the mean a certain data value is. We can also go the other way, and if we have a data value, we can find the number of standard deviations. And we get this by solving the above formulas for z. If you solve the above formulas for z, you get x minus mu over sigma, or if it's a sample, x minus x bar over s, same idea. Basically, we want to know how far away we are from the mean divided by the standard deviation. So same problem, we want to know how many standard deviations from the mean is 11. So z is equal to x, the value 11. That's our x, that's our value. Minus the mean, we said up above the mean was 8. Divided by the standard deviation. And the standard deviation we said was 1.2. So 11 minus 8, hit enter, so that your calculator knows we divide the whole thing. Divide the 3 by 1.2, we get 2.5. So 11 is 2.5 standard deviations away from the mean. How about this? How many standard deviations from the mean is 7.1? Again, that's our x value, that's our data value. So z is equal to 7.1 minus the mean, which is 8, divided by the standard deviation of 1.2. So 7.1 minus 8 is negative 0.9, divided by 1.2 is negative 0.75. It's negative, so we know then we are below the mean by 0.75 standard deviations. Why on earth does this help us? What's nice about standard deviations is they give us a standard of measurement that we can use to compare data. Let's say John has a GPA of 2.85. The average student in his school has a GPA of 3.0 with standard deviation of 0.7. We're going to compare John with Allie. Allie's school does GPA a little different and does a score out of 100. So Allie has a GPA of 77, and the average student at her school has a GPA of 80 with the standard deviation of 10. Who is the better student? This is really difficult to compare with the numbers we have because John's GPA is out of 4, Allie's GPA is out of 100. They're both below average, but how do they compare with their classmates? Standard deviation standardizes and normalizes a comparison. Watch what's possible if we look at John. John's GPA is 2.85. That's his specific value. That's our x value. His school has a GPA of 3.0. That's everybody in the school has an average, or mu, of 3.0. And the standard deviation, that's sigma, is 0.7. So John's z-score is 2.85 minus mu, which is 3.0, divided by the standard deviation of 0.7. 2.85 minus 3 is 0.15, negative. Divided by 0.7 is negative 0.214. So he's 0.214 standard deviations below the rest of his class. What about Allie? Allie's GPA is 77. That's her specific score. So that's going to be our X value for a specific score. The average student has a GPA of 80. That's our mu. And a standard deviation, sigma, of 10. So Allie's z-score is 77 minus 80 divided by 10, which is negative 0.300. Now we can compare that Allie is further below the average than John is. It would seem to suggest that John is the better student, because he's closer to the average in his class than Allie is to the average in her class. Standard deviations. How spread out is the data? How far from the mean are you? That's what standard deviation tells us. A great statistician from Russia, I'm going to murder his name, so I apologize to anyone who speaks Russian, is Chebyshev's theorem. Chebyshev. Chebyshev was interested in how much of the data could we know was close to the mean. And he found out that the proportion, we'll use P to represent the proportion, of the data observations in an interval that is k standard deviations from the mean is at least, and it could be more, P equals 1 minus 1 over k squared. This is an important formula. Chebyshev's theorem. Chebyshev. So let's say we have a set of measurements with a mean of 32 and a standard deviation of 4. How many data values fall between 24 to 40? Well, 24 and 40, those are X values. Those are specific data values. We need to know how many standard deviations away those are. So we're going to need to actually calculate the Z values. 32 is the mean. 4 is the standard deviation. So we do X is 24 minus the mean of 32 divided by the standard deviation of 4. 24 minus 32 divided by 4, that's negative 2. And you'll notice if you do it for the other value, 40 minus 32 divided by 4, that's 2 standard deviations away. So we're going 2 below, 2 above, we are interested in being within 2 standard deviations of the mean. 2 standard deviations. That's what we're going to use for our k. We want to be within 2 standard deviations of the mean. So the proportion is 1 minus 1 over 2 squared. And if I do that on my calculator, 1 minus 1 over 2 squared is 0.75. That is the proportion. 3/4 basically of the data is between 24 and 40. At least, possibly more. I didn't tell you how many data values there are. Let's say there's 180 measurements. Can we squeeze the number 180 in there? We've got 180 measurements. So of the 180 measurements, 75% fall between those values. So 180 times 0.75 is 135, at least, fall between 24 and 40. Could be more, but there's at least 135, because there's going to be at least 135 within 2 standard deviations of the mean. We can ask a similar but backwards question. What if I asked within what interval do 160 measurements fall? Well, Chebyshev's theorem talks about proportions and standard deviations. So we need to know what is the proportion 160 out of 180. 160 out of 180 is 0.8889. That's the proportion. So now we go to Chebyshev's theorem, which says we know the 0.8889 equals 1 minus 1 over k squared. Subtract 1 from everything, we get 0.1111 negative equals negative 1 over k squared. Negative to negative makes them positive. And then we'll multiply both sides by k squared. So 0.1111 k squared equals 1. Divide by 0.1111. And k squared equals 9. So k, taking the square root of both sides, k is equal to 3, and actually plus or minus 3. And what does k represent? The number of standard deviations above and below the mean. So now we go back to that x equals formula. Remember that x equals formula was our z value. We're using k in this formula, but it's the same thing, times the standard deviation plus the mean. So x equals plus or minus 3 times the standard deviation, remember that was 4, plus the mean we said was 32, and we'll get a range. When we do negative 3 times 4 plus 32, we get 20. Positive 3 times 4 plus 32, we get 44. So there are at least 160 measurements, possibly more, between 20 and 44. How about this question? Outside what interval will at most 45 measurements fall. The key word here is outside what values? Chebyshev tells us the number that fall inside an interval. So if 44 are going to fall outside, our formula is going to tell us how many fall inside. There were 180 measurements. If there's 45 on the outside, subtracting gives us 135 inside. So for our proportion, we're going to do 135 out of 180. 135 out of 180 is 0.75. So our proportion is 0.75 is equal to 1 minus 1 over k squared. Subtract 1, we get negative 0.25 equals negative 1 over k squared. Negative, negative makes it positive. Multiply both sides by k squared to get rid of the fraction. 0.25 k squared equals 1. Divide by 0.25, and you get 4. Yep. So k must equal 2. We are 2 standard deviations from the mean. So what are our x values? Remember, x is equal to z, or in Chebyshev's case, k, times sigma plus the mean. Remember, when we take the square root, plus or minus, so we have plus or minus 2, times the standard deviation, which we know is 4, plus the mean, which we know is 32. And when we do that on our calculator, we will get a range. Negative 2 times 4 plus 32 is 24. And positive 2 times 4 plus 32 is 40. So at most 45 measurements will fall, outside of this range, outside of this interval. So not within, but outside of. So smaller than 24, bigger than 40, there's at most 45 of those data values. One last problem as we wrap up here. How many fall outside of 20 to 44? Again, we're falling outside. So we're going to want to do our work with 20 to 44, but then we're going to be outside of that. So whatever we get, we're going to have to subtract to find out how many are outside, because our work is going to tell us how many are inside. Now 20 to 44, that's interesting. Well, let's just work it out. Probably not a great example, because we've seen that before, but that's okay. 20 and 24, those are our actual data values. Those are our x values. So we need to find our z values. Remember, z is x minus mu over sigma. So for our first one, z is equal to 20 minus the mean. The mean is 32, divided by sigma, the standard deviation of 4. 20 minus 32 is 12. Negative divided by 4 is negative 3. We should get the same value from the 44, just positive. 40 minus 32 over 4 is indeed a positive 3. So we want to be within 3 standard deviations of the mean. That's what we're going to use for k. Our proportion then is 1 minus 1 over 3 squared. 1 minus 1 over 3 squared is 0.8889. If we take 0.8889, which is our proportion, times the total number of values, which is 180, we get approximately 160. But be careful, Chebyshev tells us how many fall within that range of 20 to 44. We want to be outside of that range, and so we have to subtract. There's 180 total minus 160. There are at most 20 values that will fall outside of the 20 to 44 range. So we took a look at a lot of descriptive statistics in this video. So we're going to take some time to plant on that in class with a couple of labs and practice assignments. To really work on this, make sure you can do this well. Also take a look at the homework assignment, and we will see you in class with questions on displaying data graphically, finding the mean, median, mode, quartiles, percentiles, finding standard deviations, and more importantly, interpreting standard deviations. How many standard deviations are you from the mean? We'll see you in class.